All right, so this is my last lecture with you guys, and my responsibility today is to teach the first half of a portion of Chapter 8. And starting next week, Professor Robert Ryan from Civil Engineering will teach you the second half of Chapter 8 and continue with the course. All right, so let's all right, so we're going to learn about derivatives and how they're used in engineering. So we are going to start with a very elementary problem, which is that we take a ball, we elevate it to a height of 1 meter, and we reset the clock to time t equals 0, we drop the ball. All right? And we calculate the total time it takes for the ball to hit the ground. And that position is recorded at y equals 0. All right, and I have three questions for you. What is the average velocity? And what is the speed at the point where it hits the ground? And what is the acceleration of the ball? Okay, so how do you answer this question? If this is all the data I gave you, what would the average velocity be?
4.52 meters per second.
4.52 meters per second. All right, how about speed? Wait, it's not 4.52 meters per second. No, it's 4.452. It travels a meter. All right, so it's 1 divided by 0.452, which is 2.21 meters per second. Right? If it's the other way around, it's 0.452. All right, so how about speed impact? We do not have enough data points to calculate that value. Neither do we have enough data points to measure the acceleration of freedom. Okay? So what do? We repeat the experiment. And this time, what we're going to do is we are going to not just calculate the value at the first and last time spots in the experiment, but we're going to get some data at in-between time intervals as well. So at time t equals 0, it's at 1 meter. And then I have 5 sensors. And when it passes through, when it drops for 0.1 seconds, it records the position. And then it keeps recording every 0.1 seconds till the point of impact. So in addition to 0 and 0.52, we have 4 in-between data points. Okay? Now you can calculate the average velocity of each interval. So instead of going between 0 and 0.52 at one go, you break that into 5 smaller time intervals, and you can calculate the average velocity in each time intervals. Now if I ask you to tell me what is the velocity at impact, what would you do? So the velocity or speed is always the difference in position by time. You would take the last one, right? So you would take the difference between 0.4 and 0.452. All right, so velocity is change in the y position divided by change in time. So the change in time, for change in position, let's say I do the first two here. So I take the difference between the change in position and the change in time. So change in time is 0.1 minus 0. And change in position is 0.951 minus 1. Right? So that will give you the average velocity for the first interval. So I want you to similarly calculate the velocity for the last interval there. Right? So you have the position at the 2 times 0.4 and 0.452. You take the difference between the two values, which is 0.215, and divide that by 0.052. So 0.215 divided by 0.052 would give you should give you 4.13 with a negative sign. Right? So here we record all the velocities for each average velocities for each time interval. And this is really not velocity at impact. It's the average velocity for the last time interval, right? So what if I were to break this down instead of getting a total of 6 data points, what if I had 600 data points? Is the velocity at the last time interval going to change the more you divide? Or is it going to stay the same? So when we had just 2 time intervals, the average velocity was 2.21. Right? We have the first and the last, and we calculated the average velocity, and that was 2.21. Now we break this into 6 time intervals, and we calculate the time taken for the last time interval. Calculated the velocity for the last time interval. And that gives you a velocity of 4.13. So initially, the only velocity we had was 2.21. Now we realize that the velocity changes, okay? And you can calculate the velocity for each time interval. Okay, so going by this data, you would say that the velocity, the initial between 0 and 0.1 is 0.490 meters per second. Between 0.1 and 0.2, it's 1.47, etc. So the velocity between 0.4 and 0.452 is, okay, so the velocity increases as the ball continues to drop. All right, so when you divide it into 6 instead of 2.13, which is what we got when we took the total time, now we have a little bit more accurate estimate of what the velocity of impact is. Now, instead of 6 time intervals, what if I divided this into 60? Is it going to stay the same, or is it going to change?
It's going to increase slowly, but not very much.
It's going to increase slowly, but now in the limit that I have infinite intervals between the first and the last one. So I had just one interval, and that gave me a velocity of 2.13. I have 6 intervals, and this gives we see that it's starting to plateau. Now, if I had 60, this value is going to increase, but it's going to flatten out even more. If I had infinite, is it fair to say that if I had infinite time intervals, the velocity over the last time interval could be approximated as the velocity of impact? And if it was really, really, really small, it would be the actual velocity of impact. You're with me on that? And that is the concept behind a derivative. Okay? So will the answer change if you had more data points? Yes. Okay? And now we are going to use MATLAB to solve the same problem. Okay? And as always, I've posted the codes on Blackboard, and it's for you to use. Okay, so these are our variables. We enter our variables. So let's go to MATLAB. So we enter the value of y. So these are we did the experiment, and we have all these data points. So these are all our times. T is 0, 0.1, 0.2, 0.3, 0.4, and 0.452. And this is the y, or position. So we create 2 arrays. The first array is all the positions, and the second array is all the times. Okay, so let's go to MATLAB, and I have 3 codes here, 8.1, 8.2, and some examples for chapter 8. So this is for section 8.1, that's the problem I'm currently solving. So the first thing I'm going to do is I declare 2 arrays, y, which is position, and t, which is time, and I plot y as a function of time. So let's look at what the plot looks like. All right, so if you plot y as a function of time, it looks like this. So at time t equals 0, all right, it's at a certain height, and then it goes down as time increases. Now what I'm going to do is I am going to use this tool called CF tool. All right, and CF tool is a curve fitting tool. So I'm going to go to MATLAB. So this is called as a command line prompt. All right, so I told you there are 2 ways in which you can enter information into MATLAB. One is to create what's called as a .m file or a script file and run that script file. Or you could type any command you want at the command line. Right? For example, I could type 4 times 2, and it would say answer equals 8. All right? And what I'm asking you to do here is I'm asking you to type this CF tool at the command line. So let's type CF tool at the command line, and it'll open up something called as a curve fitting toolbox. Okay? And we have to import the data. So the x, we're plotting position versus time. So on the x-axis, your variable will be time. And on the y-axis, your variable will be the position. Okay? So these are those 5 black dots are the 5 points. And right now, I'm fitting a polynomial of degree 1. A first degree polynomial is a line, a linear polynomial of the form ax plus b. If I were to change that to 2, I would fit a quadratic polynomial connecting all those points, and that is of the form ax squared plus bx plus c. Or in MATLAB language, it's p1 x squared plus p2x plus 3. And for this particular curve, the values of p1, p2, and p3 are given here. Okay? So you took a bunch of points, you used the curve fitting tool, and now you have an equation that describes that curve that you see there. All right? So the equation would be, I would take these values of P1, P2. So P2 is very small. I'm going to approximate that to 0. So that's P1 and this is P3. So my equation is negative 0.4891 t squared plus 0 times t plus 1 equals 0. Right? So I would write down that equation. So this is what my equation looks like. So position as a function of time is 4.891 t squared plus 1. All right? The way the book presents that to you is, here's the experiment, and then an engineer comes and gives you this curve. So we can generate this curve ourselves. We don't need an engineer to come and tell us. And MATLAB helps you with that. All right? So if you do an experiment, you can take all those data points, you can use the curve fitting tool, and you can find the mathematical equivalent of that data. And once you have the mathematical equivalent, we can calculate everything that we wanted to very easily. Right? So that's the expression for position. And what did we do to get velocity from position? We took the value of position at 2 time intervals. All right? So velocity is nothing but change in position divided by change in time. Okay? So that's a discrete quantity. And what do I mean by a discrete quantity? It's the value between 2 points that have a finite distance between them. Okay? And one of the questions I posed was, if you have 6 intervals, you get a certain value. If you had 60 intervals, you're going to get a different value. And as you increase these number of intervals, the value is going to change, but the amount by which it changes is going to be smaller. In the limit of you having infinite intervals, you are no longer in the discrete domain, you go to a continuous domain. Right? So to explain the difference between discrete and continuous, I can give you a very simple example. All right? So this is what a sine curve looks like. That's continuous. This is the discrete equivalent of the sine curve. You see, I have a finite number of points, and there is a gap between each one of those points. That's discrete. And that's what we did when we dropped the ball. We took the data at discrete time intervals, and when you do that, you don't get the right answer because you're not connecting them with a curve, but you're rather connecting them by a straight line, like so. So there's a little bit of error that's involved here, and that's why the value keeps changing the more time intervals that you have. In the limit of you going to an infinite set of points, or the points are so close that the distance between them is infinitely small, then you go from discrete to continuous domain. So mathematically, this is how we see that. In the limit of delta t, that is, in the limit of me chopping up the time interval into infinitely small little bits, the change in position divided by change in time. So everything on this side is discrete. In the limit of delta t going to 0, discrete becomes continuous, and we write this as dy by dt. That is the derivative of time. And that is a good introduction to what a derivative is. Okay? So you drop the ball, you have discrete data set. You find out the value of position at 6 points in time, and corresponding to those 6 points in time, you have the value of position at those 6 points. Okay? And you can take the difference and get discrete values for velocity. So what that means is in that gap, the average velocity is so much. You are not able to pinpoint and say at that point my velocity is so much. You can't do that. All you can say that is between those 2 points my average velocity is so much. And that is not quite the same as velocity at impact. So what you're calculating is the velocity between average velocity between last 2 points. If you want the velocity at impact, you'll have to divide that to infinitely small number of points. And the mathematical equivalent of physically taking the time and chopping it up into infinitely small pieces is the derivative. So if you didn't have the derivative, the way you would do this experiment is, instead of calculating it at 6 points, you would calculate it at 600,000 million zillion points. And that is mathematically this. Okay? You understand the beauty of a derivative now? All right, so let's calculate this using MATLAB. Okay, instead of using the differentiation function, I am physically finding the derivative using what's called as a for loop. All right, so let's understand what's going on inside this for loop here. So I have y of t, which is all the positions, and I have a t, which is an array containing all the times, and I calculate velocity as the difference between the positions, 2 successive positions. So here I goes from 1 to 4. All right, so that is considered a for loop. So let's see how this program works. Did you learn about for loops from Dr. Bai's MATLAB introduction yet? All right, so I'll give you a detailed introduction of what for loops are. So the statement is for I equals 1 to 4. So what this means is I will take on the value 1 first, and then you go inside the loop. And what do I have inside the loop? I have v of I, which is nothing but v of 1, equals y of I plus 1 minus y of I. Since I is 1, it's going to be y of 2 minus y of 1 divided by t of I plus 1 minus t of I. So that is t2 minus t1. And that is indeed our velocity, right? So the difference in position is given by this expression, and the difference in time is given by this expression. And you store it in v1. Okay? And I have another variable, all right, and I call it time interval, or t-intv. Here I is 1, so t-intv of 1 would be t of I, which is t of 1, plus t I plus 1 minus t of I divided by 2. Okay, so let's see what I'm doing here. I have all right, t of 1, t of 2, t of 3, t of 4, t of 5, and t of 6. And at each one of those times, I have position 1, 2, 3, 4, 5, and 6. Okay, so that's the data I begin with. That's what I have on top. So once I I've calculated these two. Let's find out what happens after you execute the second line. After you execute the second line, you would go to the end, and MATLAB will ask itself the question, has the loop ended? I has to go from 1 to 4, so the loop does not end till I becomes equal to 4. So what will MATLAB do next? It will say I equals 2. And when I equals 2, you would get V of 2 equals y3 minus y2 divided by t3 minus t2. And time interval 2 would be time interval 2 plus t3 minus t2 divided by 2. Okay? Are you following me here? Yeah, so I will continue doing this 2 more times. I would become equal to 3. So what I'm doing with MATLAB is the equivalent of what I would do right here with a paper and pencil. Okay? So I would take t2 minus t1, take the difference between that, y2 minus y1, take the difference between that, and I would have delta y and I would have delta t. I would divide delta y by delta t and I would get velocity. I could do it by hand or I could do it using MATLAB. And if I did it using MATLAB, this is what it looks like. Okay? So that's the plot. See what it does? So it gives you 4 different values of velocity here and 4 time intervals. And if you compare that with what we have here, it's exactly the same. Okay? All right, so there are multiple ways in which you will be asked to do it in the exam. So there are 3 ways. Right? One is the MATLAB way. You'll be asked to do that in the MATLAB quiz. So they'll give you a set of data points and they'll say calculate velocity and acceleration, etc. So you would write a small program like this to accomplish the same thing. The second is using differentiation. So you can find out what the equation of the line is. You can differentiate that and get the answer from there. The third is the old-fashioned paper pencil way where you enter those numbers into the calculator and find out what the velocity is. Okay. All right, so now let's do the math way. So we have y of t, which is the equation of that curve that we fit. And y of t represents the position as a function of time. And if you like to calculate velocity, you would differentiate y of t with respect to time. So dy by dt would be this expression. So that quantity here, negative 9.82 times t, represents your velocity as a function of time. You can differentiate that once more, all right, and you would get acceleration as a function of time. But if I asked you to find out what is the velocity at impact, we know that impact happens at time t equals 0.452. So in this expression v of t, I can substitute t equals 0.452, and this is the answer I would get. Okay, so this is the velocity at impact. Okay? So I take the points, I fit a curve between them, I convert the discrete set of points into a continuous polynomial, I differentiate that polynomial, so that curve that we have, the polynomial represents the position, the derivative of the position is velocity. So I have an expression for velocity as a function of time. I can find out velocity at any instance of time, and if I'd like to find out the velocity at impact, I would substitute t equals 0.452 because that's the time at which the ball impacts the ground. So it would give you this answer. So this is 0.421, and what did we get when we had 6 intervals? We had 4.13. Right? You see how far off we are because the number of steps that we chopped up that time interval in was not significant enough. All right? Instead of 6, if you chopped it into 60, you would go closer to 4.43. In the limit that you chop it to infinite little pieces, you will end up with this value, which is 4.1. Okay, so do you understand all three pictures? One is the physical experiments and you get discrete data points. Step two is you would take those discrete data points and you would curve fit a polynomial passing through those data points. That polynomial will represent y of t, which is position as a function of time. You would differentiate that polynomial to get velocity as a function of time. And if you know the time that it takes to impact, you can substitute that value of t into that polynomial, into the velocity function, and you would get velocity at impact. Okay? Any questions? Okay. So if you want to find acceleration, you would differentiate velocity once more. So you would take the difference between two velocities divided by time, and that would give you what acceleration is. And it comes to 9.782. Right? So it's a free fall. We know the correct answer is acceleration due to gravity, which is 9.81. Because we had so few data points and we curve fit between those data points, our answer is slightly off. But just like that, with a very simple experiment, we are able to find out what the acceleration due to gravity is. All right? So we'll go to the next slide. And before I do that, I want to give you a few examples of how to use MATLAB to calculate the derivative. So when you take Calc 1, you'll have to memorize the derivative of a whole bunch of functions. And you will have to, right? There's no escaping that. But always have MATLAB as a backup because it's a very powerful tool to give you the answer very quickly. And it's a lot of instant gratification. When you're doing calc, you have an answer just like that, and it feels really good if you nail it. Okay, so let's say I have this polynomial like this, 6x cubed minus 4x squared, okay, plus some constant b times x minus 5. All right, and I taught you how to use symbolic variables in the previous class, and I declared this as a symbolic variable. All right, so I'm going to run this. I'm going to clear all this stuff here, and I'm going to run this, and let's see what I get out of it. Okay, so there is a function called pretty. So what it does is it writes everything in a pretty format like this. Instead of t minus 1 divided by t hat 4, it's not very nice to read, right? If I told you this is the polynomial, it doesn't look like a polynomial. It looks like a bunch of characters strung up together. But if you use this function pretty, it will put it as a nice polynomial. So the polynomial is 6x cubed minus 4x squared plus bx minus 5. And we can differentiate that. Differentiation of a polynomial is simply diff and the polynomial. So I have diff S1 here. So the first line is I declare what the polynomial is. Second line is I print, which means I output to the screen. Okay, and I do a pretty output. So I declare all polynomials, and then I differentiate the polynomial. So diff S1, diff S2, diff S3 would differentiate each one of these polynomial, and your answer would look like this. All right, so feel free to use this code for the rest of this course and also for Calc 1. And what I want you to do is, if you take your book, there's a whole table of different differentiation for different standard functions. Okay? And I want you to practice all of those using MATLAB and get comfortable using MATLAB for calculating the derivative of functions. All right, let's go to any questions on this? All right, so when you actually come back and do a lab with me, I think in week 9 or week 10, we're going to do exactly the same experiment. We are going to take 3 or 4 balls of 3 or 4 different material, a steel ball, a plastic ball, etc., and we're going to drop each one of them, and we're going to collect a whole bunch of data points. And you're going to do 2 things. You're going to use the data and calculate position, velocity, acceleration by simply taking the difference between 2 discrete points. and you're also going to learn to use MATLAB to curve fit, find the continuous equivalent of those discrete data points, differentiate that, and find out the velocity upon impact. All right, let's go to the next problem. In this problem, we're going to learn about maxima and minima of functions. So just like we do throughout this course, we start with an engineering problem and then try to understand the math behind it. So the problem is very simple. You take a ball, you throw it up in the air, and you ask yourself a bunch of questions. The questions are, how long does it get to its maximum height? What is its velocity when it gets all the way to the top? How high does the ball get? And the last question I will ask a little bit later. All right? And are you familiar with these equations from high school? Do these look familiar to you? No? These are called equations of motions. So the first one is telling you that the velocity is initial velocity plus acceleration times the time. All right? And the second one is position is initial velocity, product of initial velocity in the time plus 1/2 at squared. And that's the third equation of motion. Right? You should be familiar with this from your high school science classes. If you're not, I would recommend looking online for equations of motion. And hopefully you can memorize these three because they are very fundamental to a course called dynamics that you will take as a sophomore. All right, so we're going to use one of the equations of motion and set up position as a function of time. All right, so this is S equals ut plus 1/2 at squared. That's this equation. The second equation here, I'm using that equation because I'm tossing the ball with an initial velocity of 4.43 meters per second. So that's my u. Time is my independent variable. 1/2 at squared. Acceleration due to gravity is acting downwards, so I'm going to associate a negative sign with that. The value of acceleration due to gravity is 9.81. So 1/2 of 9.81 is 4.905, and that's how I get this equation. So this is a quadratic equation that represents as a function of time. Okay? So the first question is, how long does it take to reach maximum height? And how do you find the answer to that? Say that one more time. Take the derivative of position and find the velocity. That's right. Yep, so we will find where the velocity equals 0, and we'll see changes from positive to negative. So if that was confusing, I am going to first plot. So we use MATLAB, and we plot velocity position as a function of time. So you throw the ball, and this is what it looks like. So it goes to a certain height and comes back down. Okay, so if you wanted to find the maximum position, what would you do? Physically? That's mathematically. So if you had this curve, and I told you what is the maximum height, what would you do? You would just pick the top of this graph, all right, and you would project it onto the y-axis, and you'll find out what the maximum height is. All right, the mathematical equivalent of that is the derivative is the slope. So you calculate the derivative, and you would notice that as you go up, the slope decreases, and it gets to exactly 0 at the maximum position, and then the slope becomes negative. Okay? So there's an inflection point where the slope goes from positive to negative, and that inflection point is when the slope equals 0. Okay? So the slope of the position curve is nothing but the velocity. So as you said, we will differentiate the velocity, differentiate the position, we will get the velocity, we will set that to be equal to 0. And when we do that, you're solving for the value of t at which the velocity goes to 0. So the equation is All right, so 4.43 t minus 4.905 squared. If you were to differentiate, you would get v of t equals 4.43 minus 9.81 t. So write that down. So you can say that dy of dt equals v of t, which equals 4.43 minus 9.81 t. Okay, you're simply differentiating this expression here. You would get a linear in t. I want you to solve that linear equation and tell me what is the value of t. Very good. So you've answered the first question. All right. What time does it take to reach the maximum height? The answer is 0.452. And how did we get there? We took position as a function of time. We differentiated that, and that gives you velocity. And the velocity is the slope, or the slope of the tangent to that curve. And when velocity equals 0, you would set that value to 0, and you'll find out what t it is. So the second question is, what is the velocity at maximum height? So you have v of t equals 4.43 minus 9.81 times t. And you have the value of t at which the v becomes 0. So the value of t at which v becomes 0 is the value of time at which velocity becomes 0 is 0.453. Is that what you? 0.452. So you substitute that back into this expression, you would get the maximum height, and the velocity at maximum height is simply 0. So the answer to the second question is 0. The answer to the third question is, you would substitute t equals 0.452 into this expression. Okay? And I want you to do that and tell me what is the value you get for y of t. All right, so for position, substitute t equals 0.452. And the answer should be 1.00 something. Yep, so let's call it 1 up. Now we're going to solve the same problem using MATLAB. Okay. All right, let's see how I accomplish the same thing. Okay, so the first statement is, I declare a symbolic expression, 4.43 t minus 4.905 t squared. And that's exactly the same as this equation here, 4.43 t minus 4.905 times t squared. Okay, that is y t. I declare a variable called y of t. And then I differentiate that and find out what v of t and a of t are. So let's run this code and see what we get. Okay, so v of t is the derivative of that. Simply use diff to differentiate that. All right, I get the velocity, and I differentiate the velocity once more to get acceleration. Okay, and I plot all the answers in a pretty way. So y of t is position as a function of time. That's 4.905 t plus 4.43 t squared. And this is velocity, and this acceleration. All right. I'd like to find out t max. So I have to take the derivative. So v of t is the derivative of position, and I have to solve that expression expression, when I differentiate the position, when I differentiate the position expression for velocity, and when velocity, I get the value for t. So here's the value for t max 0.451, and that's exactly what you got with the old-fashioned calculator, right? All right, the next step is I take that value of t and I put it back into the expression for y. So the value of t at which I get zero velocity is, I call it t max. And I put the value of t max in my original equation, and I get the value for the position, which is 1.00. Okay? So all the MATLAB codes are available for you on Blackboard. The homework problems are based on exactly what I've taught today. So you should be able to do the homework problems, and you feel free to use the MATLAB to solve them, but don't simply give the answers without doing it by hand. I want you to do both. You will do both the differentiation by hand and find out what the answer is, and you can also use MATLAB to find out if your answer is right or wrong. Before you leave, let's talk about the last point here, which is the second derivative test. So you told me that the slope changes from positive to 0 to negative. Okay? Now, how do we know if this is maximum or minimum?
It's maximum when it goes from positive to negative, in the first derivative, and the second derivative is maximum.
When the second derivative is less than 0, you have a maxima. And when the second derivative is greater than 0, you have a minima. Okay? So in this expression here, what is our second derivative? So you differentiate once, you get 4.43 minus 9.81t. You differentiate it once more. The first term is a constant. Differential of that will become 0. Negative 9.81t will simply become negative 9.81. So the second derivative is negative, and that means it's a maxima. If the second derivative was positive, that would imply it's a minima. And that's your second derivative test. And that's also covered in your book. Okay? All right, so good luck with your homework, and I'll see you during the lab session.